Good morning to all of you. First of all, I compliment the School of Sciences for organizing this National Mathematics Day to commemorate the memory of Srinivas Ramanujam. We always cherish to see his contributions and the School of Sciences of this university is constantly pursuing his ideals to see the basics of mathematics it may spread to all corners of the country and abroad. Because IGNOU has got an international reach. We are having more than 35 lakh learners at present. More than 37 lakh learners they passed out. And the School of Science, it has got a great contribution in this endeavor to reach the unreached. Today, Professor M. Ramamurthy is kind enough to guide us, to inspire us, and to motivate us. A great researcher and his immense contribution in the field of mathematics will show us the path to move ahead. When we look at the biography of Srinivas Ramanujam, we find that his concentration on one particular discipline has put India on the glory, the path which he has shown to all of us. For all of us, mathematics is the core discipline. Even at the age of class 3, class 2, or even class 1, we see that the mathematics it is being taught to the learners, to the students, and at the PG level and the researchers, lots of activities they are being carried on in the field of mathematics. It is a glorious path which tells us that when we are talking about the NEP, then we see that the mathematics is a discipline which can be integrated to any area, be it in the field of commerce, be it in the field of arts, because even we know that the BSc and the BA in mathematics, MSc and MA in mathematics, even in BCom, there also mathematics is there. Even for professionals, the CA, ICWA, even the company secretaries, everywhere the mathematics is the discipline which is being taught and nurtured. If you look at the competitive examinations, there also the basics, general awareness, the general knowledge, and even the general subjects wherein the importance of mathematics is being outlined. So it has got its own importance, and the School of Sciences, they are contributing a lot in this endeavor. And they have ventured to have their first program in the post-graduation, that too in the field of mathematics. So I must compliment the School of Sciences for this endeavor. And I also welcome our distinguished speakers who has spared his valuable time, Ramamurthy ji from Queen's University, to show us the way forward in which we all can contribute significantly to those learners who are deprived. And looking into this canvas which was given under NEP, we would also like to see that how the inputs, the basic inputs of mathematics, they can be integrated to other disciplines. Of course, our own Indian knowledge, wisdom, that is also being used to strengthen the base of mathematics. Vedic mathematics is one of the areas wherein we all can contribute. And the School of Sciences is also looking into it, that how those things can be integrated in our curricula, in our teaching learning process also. I once again compliment the School of Sciences for celebrating this National Mathematics Day today and convey my sincere best wishes to all of you for this endeavor. Thank you very much. Thank you.
Thank you, sir. Thank you so much, sir.
Thank you very much.
Thank you, sir, for your inspirational and encouraging words. Today, we are very fortunate to have Professor Ramamurthy, Queen's Research Chair, Department of Mathematics and Statistics, Queen's University, Canada. I would now invite my colleague, Dr. Venkatraman, to formally introduce the speaker, and the speaker would present his talk immediately after. It's over to Dr. Venkatraman.
Dr.
Venkatraman, please share your screen and start your...
Purnima.
I would request Dr. Venkatraman to formally introduce the speaker.
I think he has not logged in or what. Give him a call, no? Hello, Shachi.
Good morning, ma'am.
Very good morning.
Artist, congratulations to school for organizing.
I know, really good.
Dr. Venkatraman is trying to share here. There is some net connectivity at his point. So he's trying.
He's there.
Good morning, Professor Shachi.
Namaskar, good morning.
Yeah, he's
Namaskar,
trying to...
Mini sir.
Namaskar, namaskar.
What's the Ramamurthy at time?
Yeah.
Not.
Why?
Different problems here. a small glitch. I'll start in a minute. मैं भी आ रहा हूँ. Okay, I'll go there and do it. Yeah.
I'm so sorry. Just in 1 minute, Dr. Venkat will start.
सब गिर रहा है.
Yeah, it's Venkat, we can see the screen. You just unmute. Dr. Venkat, your screen is appearing now. You can start. Please start.
Venkat sir, please unmute yourself.
Yes, Venkat. Screen is appearing. You please unmute and introduce the speaker.
Professor Deepika, you can please continue.
Madam, I'm not able to share the screen because I'm getting the message you are not allowed to share your screen. I don't know.
Maybe he is the administrator.
Yeah. Let's wait for a couple of minutes more and then I will start I'll introduce the speaker. Let's wait for a minute or so more.
Professor Deepika, you can share. I'm sharing the screen.
Yeah, thank you, madam.
Yeah.
I'm just starting here. Hold on.
Okay.
Cool. Let her do. Let her do. Yeah, you can please start.
Is he around, Dr. Venkatraman? He can come to my room.
He's there.
It's working well.
I'll do it. Hold on.
Venkat, please come to my system.
No,
Yeah, it's today.
You can just carry on, Dr. Venkat. Dr. Venkat.
Yeah, hold on.
Just keep on speaking. I have displayed. Presentation is there.
Okay.
Just speak. You can bring your chair this side.
Yeah, go there. Hold on.
प्रोफेसर दीपिका, प्लीज आप कंटिन्यू कर लीजिए. ऑलरेडी इट इज बीइंग गेटिंग डिलेड.
मैं करूँ? फुल स्क्रीन चले जाइए. फुल स्क्रीन.
दीपिका जी, यू आर म्यूटेड, प्लीज.
Yeah, ma'am, could you show the first slide, please? Yeah.
Next slide.
It's okay now. It's visible. So
Okay.
today,
You can please carry on.
Today we are fortunate to have Professor Ramamurthy with us. He is V. Douglas Distinguished University Professor and Queen's Research Chair in the Department of Mathematics and Statistics in Queen's University, Canada. And he is... Ma'am, could you show the next slide, please?
Yeah.
He was born on 16th October 1953 in Guntur. His brother is also a renowned mathematician. We know him as Professor V. Kumaramurthy. He's a distinguished mathematician. Both the brothers, Professor Kumaramurthy worked with Professor John Tete, a renowned number theorist at Harvard University for his doctoral degree. Both the brothers have collaborated often and written research papers, expository articles, and so many books. Next. Yeah, this is the group photograph where you see Professor Murthy and his guide, his advisor, along with the whole research team there. He has so many awards to his credit. He got Coixter James Prize in 1988. He has been awarded the Fellowship of Royal Society of Canada since 1990 till date. He's definitely Queen's Research Chair since 2002, which we have been talking since long. He has been a fellow of the Field Institute. He has got Queen's Research Prize in 2003. He has been adjunct professor in the institutions in India and abroad at so many places. He has been elected fellow of the National Academy of Sciences India in 2007. He has also been elected fellow of the Indian National Science Academy in 2008 and fellow of the American Mathematical Society in 2012. He has been awarded for excellence in graduate student supervision in 2018, and he has been elected fellow of the Canadian Mathematical Society in 2018. His area of research are L functions, sieve methods, elliptic curves, Ramanujan graphs, and combinatorics, modular forms. Yeah, these are the titles. These are the books, publications. He has published so many books in his credit. Some of them have been like these. These are the popular books which he has contributed along with his fellow mathematicians, and these all are from renowned publishers. Now he shows deep interest in philosophy, particularly Vedanta, and he has been cross-appointed to the Department of Philosophy at Queen's University, and he has this wearing title Indian Philosophy to his credit, and he published this book on Indian philosophy. So he's not only a mathematician, but having a deep interest in Indian philosophy especially. Now, Professor Ramamurthy has joined this, and I would now request Professor Ramamurthy to begin the talk on Ramanujan and his legacy. The topic of the talk is Ramanujan and his legacy. So now I invite Professor Murthy to begin the talk. So you can share the screen.
Yeah, can you hear me first?
Yes.
Okay. Firstly, I apologize for not being able to connect. I think I was using the wrong link or something. I had several emails with different links. So I think there was a bit of confusion on my part. I'm the one to blame, I suppose. So let's see if we can share the screen. How do I share screen on Google Meet? I'm not familiar with this thing.
So there is a rectangle showing an upward arrow. You just click that and share your screen. On the bottom line of tabs, you would be seeing a rectangular box having upward arrow.
Okay, let's see. A window. I have to select the screen. Okay, hold on. Is this visible now? Is this visible or?
No, not yet. Yeah, it's visible now.
Yes.
Can you see something?
Yeah, we can see Ramanujan and his legacy along with his picture and write-up.
Okay, that's good. Let me just see if I can. Let's see. View, I think, is the full screen mode. Perhaps does this work? Can you see?
Yeah, it's working very well, sir.
Oh, okay, but I can't see anybody from now. I mean, I can only see my screen.
Yeah, but we can see and we can hear and we can see your presentation too.
Okay, so you just want me to, don't you think I should be able to see somebody?
Since you're sharing, because otherwise, then you have, shared that tab only, na? Now since you have shared the whole window, so you won't be able
I see. I got it. I see. I think maybe if I let's see, if I stop sharing,
it would be difficult to switch to other slides in that case. No?
Pardon me. Should I share the whole screen, your entire screen? Is that the?
Yeah, that would be better. So you share the whole screen.
Share the whole screen. Does this? Let's see. Allow. Does this work? Is that working?
Let's wait.
Is it working to you?
Yeah, it's working.
Okay. And then I can see some people on another window.
Yeah.
Okay. I'm sorry about my technical incompetence on my part. So is that coming through?
Yeah, it's coming.
Is that so? Should I just start now, or should I try to?
Yes, please.
Please.
Is that okay? So, okay. Well, firstly, let me begin by thanking the organizers, Professor Venkatraman and others in the IGNOU Department of Mathematics, and for inviting me to speak on Ramanujan and his legacy on this National Mathematics Day. It's quite an honor. Thank you very much. So let me just begin by let me know if you're not seeing anything, because I never know what's going on. Okay, so if you're not seeing anything, please tell me. So the life of Ramanujan is really a life which is from rags to mathematical riches. And in 1999, Robert Kanigel wrote the first definitive biography of Ramanujan. But Kanigel, not being a mathematician, was unable to determine the impact of Ramanujan's work. So this is the book that he wrote, The Man Who Knew Infinity. And this book was made into a Hollywood movie, which I think most of you may have seen. I want to discuss 4 themes in Ramanujan's work Don't worry, I will not be too technical. The themes are the normal order method, the partition function and the circle method, modular forms, and finally the modular forms. So I just want to touch these 4 things, which I think really transformed mathematics. Okay. The story of Ramanujan is from humble beginnings in this tiny village in Tamil Nadu. He was born on December 22nd, 1887. And to a large extent, he was self-taught and became a universal genius with his fundamental contributions to number theory. This talk is a panoramic view of how this came about. So this is the school that Ramanujan went to. It looks like any ordinary village school. And it's amazing and impressive that Ramanujan could rise from such humble beginnings to stellar heights. His childhood was very eventful in the sense that he taught himself by reading books. One book is Plain Trigonometry by Loney. He did this at the age of 12. And if you look at this book, it looks like any old trigonometry book. But on the other hand, there's more than trigonometry in this book. It also has rudiments of calculus. So at the age of 12, he mastered calculus. But the book that really changed his life is this book called Car Synopsis. It's a book used by students, PhD students at Trinity College to prepare themselves for the PhD exam. It's called the Mathematical Tripos. And students would study this book, I suppose, review the main theorems and prepare themselves for the examination. But Ramanujan looked at it as a book where he would use it as a tutorial, self-taught manual, where he would take each theorem and look at it as a something to be proved, and he actually proved it. So the book that changed his life is this book called Carr's Synopsis of Pure Mathematics, which he borrowed from the local library. And here, I suppose this incident underlines the importance of libraries and keeping good books in the libraries. And because he was too poor to buy paper, he would use his slate to work out things and then rub the slate with his elbow. And everyone spoke about Ramanujan's bruised elbow because he got it by erasing his slate. The college days were also marked with some episodes. In 1903, at the age of 15, he was admitted to government college in Kumbakonam, but unfortunately he failed his exams, and he spent too much time on mathematics and neglected the other subjects. So for Ramanujan, he had to admit that he didn't pass the program. And then he moved to Madras, now called Chennai. He failed in Kumbakonam, so moved to Chennai, 1905, and he enrolled in this Pachiyappa's college. There's the entrance. But unfortunately, he failed again due to his neglect of his non-mathematical subjects. So I suppose what this shows us is failure is no indication of inability. Now, so because he failed at all these exams and he didn't get a degree, he had to take up a job as a clerk in the Port Trust office. So he did that. But in the meantime, in between his menial chores, he would be tutoring a lot of the students in mathematics and somehow eked out an existence. But he found leisure to do mathematics and jotted down his results in his famous notebooks. These notebooks are now in the Chennai Ramanujan Library. I think Chennai Ramanujan Museum, that was put together by Professor Srinivas Rao of math science. So these notebooks now, I keep telling my students that the importance of having notebooks is very, you don't have to be Ramanujan to have notebooks. You should have a notebook regardless as a means of learning things. Knowledge is not in books. Knowledge is only accessible when you learn it yourself and put it somehow into your mind and use it. So even though the knowledge may be in books, if it's not in your head, you really don't have it. So the only way to get it into your head, perhaps, is to first put it down to a notebook. So that's why these notebooks are very important. Okay, now a lot of people think that it was G.H. Hardy who made Ramanujan famous on the world stage, but I just want to set the record straight and tell you that two Indian mathematicians in Chennai were actually instrumental. One was Ramchandra Rao and the other one Srinivas Iyer. Both of these at the Madras Port Trust office, they were instrumental in enabling Ramanujan to go to England. But first, they were discussing many mathematical ideas with him in 1910. I have a suspicion it was Iyer who edited Ramanujan's letter to G.H. Hardy for correctness of the English language, etc. So it was also Iyer who suggested to Ramanujan that he write to G.H. Hardy. And it seems that Ramanujan wrote to three other mathematicians before he wrote to G.H. Hardy, his now famous letter of 16 January 1913. And the other mathematicians who he wrote to, well, two of them never responded. The other one responded in a very rude fashion, saying that you better go back to school and learn how to write, or something to that effect. So, but the letter to G.H. Hardy is actually very famous. The letter opens up with a very simple paragraph, introductory paragraph, and then goes on page after page with formulas. So this is a picture of G.H. Hardy, and he got this letter from Ramanujan, small paragraph with basic introduction, but then right after that, page after page after page, formula after formula after formula for the next 10 pages. It's a very unusual letter. I don't think there's any such letter in the history of the world. Okay, so here's a sample page of the letter. You can see, this, of course, it's typed. This is typed in the complete works, the collected works of Ramanujan, but the handwritten version is also available in the museum. When Hardy received this letter, he couldn't decide if it was written by a crank or a genius. And the theorem, there were about 120 theorems stated in the letter. Now, I want you to pay particular attention to entry number 7, because entry number 7 is going to show up later in the talk. It has to do with the coefficient of x to the n in the inverse of the power series expansion. And I want you to pay attention to the fact that there's a hyperbolic cosine pi root n and a hyperbolic sine pi root n over pi root n in that formula, because it's going to show up. This is the 1913 letter of Ramanujan before he went to England. Here are some more extracts from Ramanujan's letter. So you can see page after page of formulas. One more page after formulas.
Ram,
Yes?
it's tiny on my screen. Can you make it a little larger if you're going to want us to appreciate that?
Oh, okay. Well, okay. Is that better?
Better? No.
Oh, how about that?
Yeah, that's better.
Okay, well, maybe I will actually go into full screen mode.
Yeah, for this bit at least.
Oops, okay. Oops, I have to, sorry, I'm sorry, I disconnected, I think.
No, it's there.
Now it's better. Now it's better.
Is it better?
Better now. It's better.
Yeah, better now.
Oh, it is? Oh, but I can't see anything. It's better for you now?
Yes, somewhat.
Oh, how do I stop sharing? Just for, stop presenting. Let me just do that.
I think we can read this. Yeah.
My thing has, my computer has frozen. Can you hear me?
Yeah, we can hear you. Frozen and all.
Yeah, my computer's frozen. Sorry about this.
No, it'll come back. It'll come back.
Can I?
Continue. Please
Yeah,
continue.
carry on. Now
Oh
we
yeah,
can
but
see
I
you.
can't seem to carry on. That's the problem. I mean, my screen is not.
Sir, you stop the screen sharing and then again reshare.
Yeah.
this.
How do I stop screen sharing? That's the problem.
Okay.
Can I log out and log back in? I don't know.
So we can see your screen. I don't know what problem you're facing. I mean,
What problem I'm facing is I'm not seeing my part of the screen. That means I'm not able to move anything.
is it?
Hmm. Yeah, I don't see my screen. I mean, I don't see.
Just try up and down arrows from the.
I think just try to escape and then come try again.
Try to escape. Okay, okay. I escaped. Okay, thank you for that.
Yeah.
Let me just let me now. Can you see that? Can you?
It's visible.
Yeah. Now it's gone really tiny.
Yeah, well, don't worry about that. That's not the point. I think that, I'm going to
Madam,
stop.
please bear with that.
Pardon me?
I'm telling madam to bear with that and let's continue.
So okay. Then what I'm going to do is I'm just going to try this full screen mode. Oops, I think, no, sorry about this. Yeah, let's just continue then. Well, I want to, can you see the screen now? It's something?
Yeah, it's...
Okay, fine. Let's just kind of continue. There are these formulas. Let's just not worry about too many details of the formulas. I admit that they're very interesting formulas, but there's one formula that I want to highlight. It's a formula for the number of primes. This one. This formula is actually due to Riemann, and the paper was written in 1859. It was written in German. Ramanujan couldn't have possibly read that paper. And so he must have derived this thing by himself. So Hardy's reaction, he lost sleep that night. He invited his colleague Littlewood to come over and have a look at Ramanujan's letter. So let me try the full screen mode, if you don't mind. And I think it might, does that help? No, oops, that doesn't help either. Okay, so that's not helping. Are you able to see this page?
Yeah, Hardy's reaction is visible just now.
Okay, good. Okay, I'm just going to continue like this. Google Meet is not something I don't normally use. I think I'm not very comfortable with this, but anyway, let's just make sure that you can see something. I will try to give the slides to Professor Venkatraman afterwards so that people can have access to them. Because you may want to read them again. So anyway, Hardy got this letter and he couldn't sleep that night. He invited his colleague Littlewood to come over and have a look at Ramanujan's letter. And after 3 hours, well past midnight, they concluded this was the work of a genius. And so Hardy writes, a single look at them is enough to show that they could only be written down by a mathematician of the highest class. They must be true, because if they were not true, no one would have the imagination to invent them. It's a very interesting line. So Ramanujan sails for England from 1914 to 1917. He had fruitful collaboration during a short span of 3 years. He writes 30 papers. Can you imagine that? 30 papers in a short span of 3 years. 7 of them jointly with Hardy. So we'll highlight here 3 of these papers because I believe they changed the course of 20th century mathematics. The 3 papers are the normal order method, the normal number of prime factors of n, the circle method, the asymptotic formula for the partition function, and finally, the famous Ramanujan conjectures on the tau function, written in 1916. The normal order method is the following. If you let omega n be the number of distinct prime divisors of n, you want to study how it behaves. Now, omega of n is 1 if and only if n is a prime power. So it behaves rather irregularly, but the question they were asking themselves is there any regularity in the behavior of omega of n? And what they found is, statistically speaking, that it's usually log n. So omega of n taking small values is an aberration. Seems to be that the average value of omega of n is log n. And so they've proved this remarkable theorem called the Hardy-Ramanujan theorem that omega of n usually is log n and deviates from it by about square root log n with probability 1. This is their theorem. This theorem was a milestone paper. It was innovative for its elementary use of the sieve method. But the real culmination of this was in the paper itself. There are indications that there's a deeper law governing the behavior of omega of n. And this is what's called the Erch-Katz theorem. Omega of n minus log n over square root log n is normally distributed. This is an amazing, the The normal distribution is something that everybody's familiar with. It's 1 over square root 2 pi e to the minus t squared over 2 dt. That's the normal density function. And this is the famous Erdős-Katz theorem. So this is a culmination of the work of Hardy and Ramanujan. Erdős and Katz proved this in the 1940s, much long after Ramanujan's death, unfortunately. But so it's an interesting chapter because it opens up a new subject in mathematics called probabilistic number theory. Their second paper involved the partition function. It's the number of ways of partitioning n. So if I want to write 4, I can write it in 5 ways, as 1 plus 1 plus 1 plus 1, or 1 plus 1 plus 2, 2 plus 2, 1 plus 3, or simply 4. So these are the ways of partitioning the number 4 into pieces. The ordering of the summands is irrelevant. So P of 4 is 5. And so every partition then can be factored uniquely as how many 1s did I use? Let's say K1s. How many 2s did I use? K2s. How many 3s did I use? K3, dot, dot, dot. So this is a factorization of this partition. And then that using this factorization, one can write down summation P of n x to the n is product k equals 0 to infinity of 1 over 1 minus x to the k. So that formula, by the way, is due to Euler. The question that Ramanujan and Hardy were asking themselves is, can we find a formula for P of n? And so this paper is a very interesting paper. It's considered the basis of what's called the circle method. And they managed to show that the partition function grows exponentially, and the exponential growth is very precise, e to the pi square root 2n over 3 divided by 4n square root 3. And in 1937, Rademacher derived an asymptotic expansion. So 20 years after the Hardy-Ramanujan paper, Rademacher shows, here's Rademacher, he shows that there's an explicit formula for the partition function. And notice the appearance of the hyperbolic sine function in the Rademacher formula. Now, if you remember in the first letter of Ramanujan to Hardy, there was this formula that I highlighted, and there were hyperbolic sines and hyperbolic cosines. Ramanujan was well aware of this behavior, but somehow Hardy thought the asymptotic formula was better than the explicit formula. So the functions that appear in the Rademacher formula are Dedekind sums, some certain exponential sums, and not really terribly important to know what these are, but the only important thing to know is that there's an explicit formula. And if you look at, as I said, in that letter, there it is. There is the 7th entry in the first letter of Ramanujan, where he's trying to figure out the coefficient of a certain inverse of a power series, and the hyperbolic sines and cosines appear. And if you check the Rademacher formula, it's very similar. So Selberg is musing over this funny episode. In 1937, he says, he was studying Ramanujan's papers, number 36 in particular, in which the formula of Rademacher, Ramanujan's paper with Hardy, and he himself had arrived at Rademacher's formula. And then he says, it always seems strange to me that Hardy and Ramanujan did not end up with this formula, and I believe firmly that the responsibility for this rests with Hardy. Now, there's a lot of humor, sarcasm in this quotation. One point here is that there was an attitude, I suppose, to some extent, that when Ramanujan came to England, that he should be educated, whatever that means, and in rigor, etc., etc. And Hardy, being an analyst, he had a certain analytical way of looking at things, whereas Ramanujan was more of a number theorist, and he had an arithmetical way of looking at things. So this is the contrast between the two. And perhaps Hardy's personality and taste allowed him to emphasize the asymptotic behavior rather than the exact behavior. And Selberg says the responsibility for this gap lays with Hardy. It's an interesting comment. Now, in January 2011, Brunier and Ono discovered what's called an exact formula, which expresses the partition function as a finite sum of special values of weak Moss forms. Now, weak Moss form, I'm going to just mention to you, is a Mach modular form. See, the Mach modular forms that I'm going to talk about at the very end, this is one of them. If it's evaluated at CM points in the upper half plane, it turns out that there's an explicit formula. Here's a picture of conference that I attended in Urbana 2003. There's Brunier and there's Ono. The other mathematicians are Youngjo Choi, Masabu Kaneko, and Winfred Conan. So we were all there giving a workshop, mini courses in modular forms at the time. And this is a very nice development. It gives you an explicit formula for the partition function in terms of special values of these Moss forms. And I was excited by this particular paper of theirs. And so in joint work with my postdoc, Michael Dewar, we managed to show that that explicit formula of Brunier and Ono can be used to derive an explicit the Hardy-Ramanujan asymptotic formula. So that's without using the circle method. That's one thing. And then in 1997, actually, there was another proof using the central limit theorem. So here we have a connection to probability theory. Some of the students that may be listening here were maybe at my course, mini course in Prayagraj at the Harishchandra Institute, where I was trying to talk about the interaction between probability theory and number theory. So here's a case in point. The central limit theorem is one of the most important theorems of mathematics. It's a theorem of probability theory, and it turns out the central limit theorem can be used to prove the Hardy-Ramanujan theorem on the partition function. So the generating function for the partition function, as I mentioned earlier, was due to Euler, and what Hardy and Ramanujan notice is that if you start putting roots of unity into this thing, it's an interesting, has singularities, and it can be related to what's called the Dedekind eta function, which is a modular form of weight 1/2. And this means that the modular form transforms according to these so-called modular transformations, A, B, C, D. Eta of A tau plus B over C tau plus D essentially turns out to be C tau plus D to the half times eta of tau. But there is a complicated epsilon factor, which is a 24th root of unity. This is an interesting fact. And Ramanujan noticed that if you take the 24th power, that root of unity disappears. And this motivates him to write this paper on the tau function in 1916. Now, his paper was studied by Mordell, who proved 2 of the 3 Ramanujan conjectures. Later on, it was developed by Erich Hecke, then by Lehner, and then by Atkin. So we have these 4 people who are responsible for the theory of modular forms in the 20th century, and they're all building on the work of Ramanujan in the 1916 paper. So the delta function, which many of you may have some familiarity with, is the 24th power of the Dedekind eta function, and it's defined by this power series. Tau n q to the n is the infinite product, q times 1 minus q to the n to the power 24. And Ramanujan made observations about what these coefficients look like, and he noticed that he computed hundreds of these coefficients. And as you can see, the numbers get pretty big rather quickly. And for us mortals, we don't see patterns in these numbers, but Ramanujan saw patterns in the numbers, and he made these conjectures that tau is a multiplicative function, it satisfies a second order recurrence relation, and finally, tau of p is less than 2p to the 11 over 2. So these are the famous Ramanujan conjectures. And I told you in the previous slide that Mordell managed to prove the first 2, but the third one was mysterious. These are called Ramanujan conjectures. The third one was finally proved by Pierre Deligne as a course of his work on the wave conjectures, and Pierre Deligne was awarded the Fields Medal for solving the last conjecture of Ramanujan. Now, Hardy was never really interested in the tau function, and he says so to kind of somehow. In the 1936 lectures that that Hardy delivered about Ramanujan at Harvard University, he made some comments about the tau function that have become famous. He says, we may seem to be straying into the backwaters of mathematics, but the genesis of tau n as a coefficient in so fundamental a function compels us to treat it with respect. So notice, he says, we may seem to be straying. He didn't say we are straying. We may seem to be straying in the backwaters of mathematics. But at the same time, he says tau n is an important function. We should treat it with respect. Okay, that's good. But Andre Weil, when he talks about Hardy in his 1972 writ lectures, he makes several pronouncements on what analytic number theory is and then pounces on Hardy. He says, Hardy's remarkable comment is, we seem to have drifted into one of the backwaters of mathematics. No, he didn't say that. We may seem, he said. He didn't say we seem to. He said we. So you have to really check the quotation. To him, it was just another inequality. This is Andre Weil. He found it curious that anyone can get deeply interested in it. No, he didn't say any of the kind. In fact, he becomes apologetic and explains that in spite of his apparent lack of interest of this problem, it might still have some features which made it not unworthy of Ramanujan's attention. So this is a very cruel, I would say, assessment of Hardy's take on the tau function. And if you check the records of who said what, these statements are inaccurate. And so in all fairness to Hardy, I think Hardy's statements were that it seems to be unimportant, but it isn't unimportant. So I think twisting it in this fashion is not proper. But again, let me give some credit to Weil on his remarkable Weil conjectures. He says in 1947 in Chicago, I felt bored and depressed. And not knowing what to do, I started reading Gauss's 2 memoirs on biquadratic residues, which I have never read before. The first one deals with the number of solutions of ax to the 4 minus by to the 4 equals 1 over finite fields, and the second one with ax cubed minus by cubed equals 1. I noticed similar principles can be applied to all equations of the form. These are called diagonal surfaces of various kinds, and this implies the truth of the so-called Riemann hypothesis for these diagonal equations. Now, the key idea for the third conjecture, remember the third conjecture was tau of p is less than 2p to the 11 halves, is actually Galois theory. There exists a Galois representation, rho going from GQ to GL to ZL, such that the trace of the Frobenius automorphism is exactly tau of p. And Dillon proved Sayre's conjecture and related this to the Weil conjecture, thereby showing that Ramanujan's conjecture is a consequence of the Weil conjecture. And now this opens up a nice window of new avenues of research, which I explored jointly with my brother Kumar. The existence of the analytic representation allows us to study the divisibility properties of the tau function. For example, how many prime divisors does tau have? I mean, remember the Hardy-Ramanujan theorem was about the number of prime factors a random number has. And now, if we think of tau of p as behaving randomly, we would like to inquire how many prime factors does it have? And it turns out that maybe it has log p. Who knows? It would be infinite if Lamar's conjecture is false. So there's a conjecture that tau of p never vanishes. And this is an open problem for the youngsters who are listening to this lecture. There are lots and lots of open problems concerning the tau function, and it might be interesting to explore them. So one such conjecture is what's called Lamar's conjecture, that the tau function never vanishes. Another open question is, are there infinitely many prime sets if p divides tau p? Now, these may look like, cavalier questions, but they're in fact very profound questions connected with algebraic geometry. Now, what Kumar and I managed to do about 10, 15 years ago is that we showed that the number of prime factors of tau of p is, again, log p with a standard deviation of root log p, and then there's an Erdős-Katz type theorem where you have the normal distribution showing up again. The only catch in our work is we had to assume the generalized Riemann hypothesis in order to get this result. And so here's an open problem. Is it possible to get rid of the Riemann hypothesis at all, or even a quasi-Riemann hypothesis, which can be used to prove this theorem? This is an open question, and I put this in front of this is Kumar and this is myself. So we did this about 20 years ago, and to this day, we don't know how to get rid of the Riemann hypothesis. Now, after this Ramanujan conjecture proved, Sato and Tate started to think about the distribution of tau of p divided by 2p to the 11 halves. Now, according to Ramanujan, that thing has absolute value 1. So that's a number between -1 and 1. Question is, how are these angles distributed? And this was discussed by Sayre as well. And the three mathematicians noticed that perhaps this number, tau of p divided by 2p to the 11th halves, is actually equidistributed, not with respect to the Lebesgue measure, but to this what's called the Sato-Tate measure. You modify the Lebesgue measure by this 2 times 1 minus x squared square root divided by pi. And this is often called the Sato-Tate measure. There's a dual thing called the vertical Sato-Tate measure, conjecture that Sayre had formulated. He proved it actually in the case with eigenvalues and Hecke eigenrooms of weight k and level n, that they are equidistributed with respect to a similar measure, but a little bit more complicated, one for each prime p. So you can see this is a kind of weird version of the Sato-Tate measure. It's often called a p-adic measure. And with my former PhD student, Kaninika Sinha, we managed to show that there is indeed an error in this thing, which we can fine-tune, and we can describe the distribution of these coefficients in this angle with respect to a precise error term. Now, this error term has since been improved by Sarnak and his students. So what about the classical Sato-Tate conjecture, the Sato-Tate about the tau of p over 2p to the 11 halves being equidistributed? Well, that's now been proved. It's an amazing thing, isn't it? It's now been proved by Barnett, Lamb, Geraghty, Harris, and Taylor in 2011. And tour de force of the Langlands program, algebraic geometry, and analytic number theory, and algebraic number theory. So a lot of stuff that goes into their stuff. Their result applies all these tools. And now what Kumar and I noticed was that this resolution of the Sato-Tate conjecture allows us to go back to the tau function and discuss what's called the maximal order. So we can figure out the precise maximal order. This was a open conjecture for a long time made by Rankin, that tau n should be less than n to the 11 halves times exponential of this log 2 log n over log n. And for infinitely many n's, it goes the other way. So the precise maximal order now can be determined using these results of the Sato-Tate conjecture, which is now a theorem. And in addition to that, you can also go and talk about what are called non-abelian versions of the Chebotarev density theorem. I will not go into details, but I'll just flash this slide. This is some work that I did with my brother Kumar. And there's more work to be done, so I'm putting this up for students who are perhaps interested in questions of this nature. Now, let me finally enter into the last chapter of Ramanujan's work. Ramanujan started becoming ill in England at the end of his life, at the end of his stay. And are you able to see me still? Okay. Are you able to see the slides still?
Yes, sir, it's clear.
Oh, okay, good. Because there was some funny thing that happened on my computer. Okay, so Ramanujan, in the spring of 1917, Ramanujan contracted tuberculosis and was admitted to a nursing home in Cambridge in England. And he showed some improvement in the fall of 1918, was elected to the Royal Society at that time. And in 1919, he started to recover enough to return to India, but sadly, after coming back, he passed away on the 26th of April, at a very young age of 32. Now, while he was in a sanitarium, this story, interesting story about the number 1729, who can fail to talk about this number in a talk dedicated to Ramanujan? This number is probably the most famous number, 1729. Interesting story is when he was ill in a sanitarium, Hardy came to visit him in a taxi with the number 1729. And Hardy enters the room and says, I just came in a taxi number 1729, which looks like a very dull number. I hope it's not a bad omen. And Ramanujan replies, on the contrary, it's very interesting. It's the smallest number that can be written as the sum of two cubes in two different ways. So here they are. 1729 can be written as 1 cubed plus 12 cubed and 9 cubed plus 10 cubed. And Ramanujan says these are the only ways you can write it as sum of two cubes. It's the smallest such number. And so he knew it right off the bat. And that impressed Hardy, which also shows that Ramanujan had intimate knowledge, intimate familiarity with many, many numbers. Now, Hardy really shouldn't have been surprised by this 1729 because you see it appears in the delta function. See the denominator there, 1728. That's the fact that 1729 is one number away from 1728 is not an accident. It has a kind of a profound connection to this delta function, the J function, all sorts of modular functions that Hardy should have been familiar with. Now, on his deathbed, literally on his deathbed, Ramanujan started scribbling furiously about a new theory called the theory of Mach theta functions or Mach modular forms. And practically nobody understood what these were at the time. Hardy certainly did not, because they don't appear in Hardy's lectures in Harvard University, the 12 lectures on Ramanujan. He doesn't make any serious mention of Mach theta functions. It took mathematicians 80 years to formulate precisely what Ramanujan meant by these things. And in modern language, these Mach modular forms fit into a neat exact sequence with classical modular forms. So here, m sub 2 minus k is the classical modular forms of rate 2 minus k. M sub k shriek is this weak holomorphy modular forms. And then you have what's called a shadow map of G star. It maps G star into a classical modular form. It's the shadow map, that's what it's called. And the Mach theta functions are really Mach modular forms of weight 1/2. And because the classical theta function, as you may know, is a theta function, is a modular form of weight 1/2. So Ramanujan was looking at generalizations of modular forms in this fashion. And Hardy thought that all was well, unfortunately. On 12 January 1928, received a letter saying from Ramanujan that he had discovered new functions. These are now the subject of current research, and the Boonier-Ono work that I talked about earlier really does use Mach modular forms. And Freeman Dyson, when he heard about these Mach theta functions, he says, these theta functions give us a tantalizing hints of a grand synthesis still to be discovered. It should be possible to build them into a coherent group theoretical structure analogous to the structure of modular forms, which Hecke built around all theta functions of Jacobi, and this remains a challenge for the future. And I think this is slowly coming up now, and we have a better understanding of what almost 100 years after Ramanujan, about what these Mach theta functions or Mach modular forms really are. And there seems to be some connections to theoretical physics as well. And I saw several papers talking about black holes and string theory and Mach theta functions and Mach modular forms. So there's a lot of connection to that. I can't say I understand everything of those papers. Now, let me conclude with some remarks that Hardy made about Ramanujan. It's actually, when I read this or muse about this thing, especially this paragraph of Hardy, it brings tears to your eyes. It's a very interesting, emotional statement. Hardy was a solitary man, and I think he had two great collaborations in his life. One was with Ramanujan, the other was Hardy, Littlewood. And I think, the British culture as it was in those days, perhaps even now, who knows, is a very kind of formal culture. And Ramanujan was the exciting episode in his life. So he says, in all fairness, I have to put this in front of you. He says in his 1936 lectures, Hardy began his lectures by saying, I have to help you to form some sort of reasoned estimate of the most romantic figure in the recent history of mathematics. The real difficulty for me is that Ramanujan was, in a way, my discovery. Now, keep in mind, this is not an egotistical statement. I think this is a fair assessment. I did not invent him. He says, like other great men, he invented himself. But I was the first really competent person who had a chance to see some of his work. I'm getting echo. Are you able to hear me?
Yeah, we can hear you.
Yeah, you're audible, sir. Yeah.
Okay, I seem to have echo of some kind. Anyway, okay. So he says, I did not invent him. Like other great men, he invented himself, but I was the first really competent person who had a chance to see some of his work, and I can still remember with satisfaction that I could recognize at once what a treasure I had found. Isn't that amazing? And he says, and my association with him is the one romantic incident in my life. The point is, You see, there's always, as I keep telling my students, you have to have a romantic relationship with mathematics in order to really do it well. So there's a lot of romance that we don't teach in classrooms. And that comes with somehow understanding things intimately. And then this is a really remarkable passage of Hardy, rather sad, actually. So let me conclude my presentation with a famous quotation from Aurobindo, which seems to sum up the personality of Srinivasa Ramanjan. On a height he stood that looked towards greater heights. Our early approaches to the infinite are sunrise splendors on a marvelous verge. While lingers yet unseen the glorious sun, what now we see is a shadow of what must come. Notice the allusion to shadow in the Mach modular forms. So thank you very much for your attention. I'm sorry for the technical glitches, but hopefully next time I'll do a better job. Thank you.
This was excellent. Thank you. Thank you, Professor Ramamurthy, for giving us an insight into the extraordinary genius of Srinivasa Ramanujan. As you know, the program is going live, so I've got one query. I think we can request you to address that, since you have written a book on Indian philosophy. So our audience is eager to know some gist of that book or some Indian philosophy related to maths education. If you can say a few lines about that.
Absolutely. So I got interested in Indian philosophy because when I studied the Upanishads, I started seeing that essentially the undercurrent of Indian philosophical thought has always been an answer to the question of how the mind works. The mind is the instrument of our knowledge, and so we're asked to learn things, discover things, and so on and so forth, but we are never told anything about the instrument and how to sharpen this instrument. So my interest in yoga, Indian philosophy, etc., was motivated by trying to understand Indian philosophy's answer to the question of how the mind works. And so, of course, as you know, modern science says it, Indian philosophy says it, that we only use a fraction of our mind and our mental powers, and that there's a way to increase the power of the mind through discipline, etc., etc. And so in that context, I'm more interested, actually, more than mathematics in some sense, more interested in how the mind is working and how do we make discoveries. And whether it doesn't matter what field that we would make discoveries in, whether it's mathematics or arts or humanities or whatever it might be, it's the mind, isn't it, after all, that we are going to be using. And so how to sharpen this. And I find I have not finished my studies on Indian philosophy yet. It seems to be anantam, infinite in nature. So did that help?
Yeah. Professor Verma, would you like to say something? Please unmute. Please unmute, madam.
Yeah, please. Thank you very much, Professor Ramamurthy, and we are very thankful to you to sparing some of your very valuable time, and I am sure that you are having a lot of today, and it was very inspiring, sir, and especially your remarks about every time. I think we have been in this forum, we have been trying this thing to give Ramanujan this thing, but each speaker add to that this thing in every talks and this thing. So our students are really getting benefited by that, and especially your remarks about central limit theorem and this thing. That is, I'm sure the students will definitely go, and we have some of our research students also who are interested in working in number theory. So I'm sure that this will benefit. And as our Vice Chancellor has said that this our students is in lakhs of this thing, and I'm sure that they all will benefit from your talk. And it's a very good this thing on, and I'm really glad to see more mathematicians like Professor Ajit Ibal Singh, Professor Praveen Sinclair, and all other mathematicians joining you in our this venture, and they are all. I'm very thankful to all of them, and I'm sure that if they want to interact with Professor Ramamurthy, please, madam, and yeah.
So now,
yeah, and any other queries from the students?
Yeah, our director would like to say something.
Thank you, Professor Ramurthy ji, for an excellent lecture. I saw that movie, Man Who Knew Infinity, but then many queries were left unanswered. But with your talk, I could satisfy myself with all those queries being answered. Thank you so much. In future also, we shall look forward to your inciting lectures, sir. Thank you, sir.
Oh, you're welcome. Yeah.
Thank you, sir. So now the program is ending, and it is such an honor for me to get the opportunity to propose vote of thanks to all dignitaries present in this webinar on the 135th birth anniversary of great Indian mathematician Srinivasa Ramanujan on the occasion of National Mathematics Day. Now, on behalf of School of Sciences, IGNOU, we feel proud to extend a warm gratitude to all the dignitaries attending this online webinar. We would like to express our deep sense of gratitude to esteemed speaker, Professor Ramamurthy, for gracing the occasion with his radiant presence and genius contribution to make this webinar a success. We trust that everyone present here must have immensely benefited from the same. We would like to wholeheartedly extend our sincere gratitude to our Honorable Chairperson, Professor Nageshwar Rao sir, for his guidance and leadership and sparing time from his extremely busy schedule to grace this event of national pride. Thank you very much, sir, for sharing your inspirational and encouraging words on this important day. We would like to extend special gratitudes to respected Professor Meenal Mishra ma'am, Director, School of Sciences, for providing all the necessary administrative and academic support to make this webinar a success. We also extend our sincere gratitudes to the Director, Center of Online Education, IGNOU, for live broadcast of this prestigious event on YouTube. We also extend our special gratitudes to respected Shri Rajesh Sharma ji, CPRO, IGNOU, for broadcasting the live event on IGNOU official Facebook page. And our heartfelt gratitudes to Shri Vishwanathan ji, Deputy Director Graphic Unit, EMPC IGNOU, to design this beautiful poster for the webinar. In the last, I would sincerely gratitude to the faculty members of School of Sciences and the office staff who rendered their voluntary services since last few days to organize this webinar in a successful manner. Once again, thank you very much to each of the esteemed dignitaries to make this event a success. Thank you. Thank you very much. Thank you.
Thank you very much, Professor Ramamurthy, and yeah.
Thank you, sir. Thank you so much. Thank you
for us, sir.
Thank you for inviting me. Yeah, thank you.
Thank you.
Thanks.
Yeah.